Okay, sorry about the delayed start. Hi, everybody. I am Swarat Chaudhuri from the University of Texas at Austin. And I'm here with my fellow speakers, Armando Solar-Lezama from MIT and Atharva Sehgal, who's a grad student at UT Austin. And we'll talk about neurosymbolic programming. Before we really get into neurosymbolic programming, let's talk a little bit about where programming is going. And whether or not you like it, it seems pretty clear that we are careening towards a world where machine learning is going to be everywhere. You're going to have software with learning abilities broadly dispersed in human societies. That software is going to constantly collect data, and there are going to be learn modules and also large chunks of the code that constitute these applications. That's going to be written by machine learning models themselves. Now, of course, this has a lot of good things about it. For example, there are clearly some kinds of tasks that you can solve using machine learning very effectively. Think image recognition that you can't easily write normal code for. There is a simple programming interface for a lot of tasks. You could imagine, now just specifying the data and then learning the code out of that. Machine learning models are often more portable, agile, easier to bake into silicon, predictable runtime, and memory consumption. These are all arguments that proponents of widespread machine learning, for example, Andre Karpathy, who wrote this famous blog post called Software 2.0. These folks have made points like this for a long time. And so here in the picture, he shows that, if you think of traditional programming as being just these sort of individual point solutions, now you can imagine in the machine learning world just specifying a very large space of computations using data, and then you have an algorithm just go and search for an implementation that fits this data well. Now, of course, in the PL community, we have also had similar pictures for a long time. In particular, program synthesis, the motivation was very similar. We are going to have specifications of various sorts, and then the computations, the implementations are going to be discovered automatically. And what we'll actually argue in this tutorial is that there's this emerging body of methods that can bring together the best of those program synthesis methods from the PL universe and these emerging or these ideas from the machine learning world. Now, in order to go there, though, we have to talk about what is wrong with this software 2.0 vision that folks like Karpathy and also other deep learning proponents that they've been advocating for. So one big problem is that machine learning often just doesn't work all that well. And the reason is that you are just learning everything from data in the contemporary state-of-the-art machine learning models. And as a result, you might be learning all sorts of weird things, especially in the edge cases, that are just not the right behavior. And there's now this whole genre of content on the internet where people post various sorts of bad outputs that come out of ChatGPT. I'm not going to go into the details of what this one is saying, but let's just say that in terms of reasoning, models like ChatGPT, they're not all that great, at least yet. And this is because, again, who knows what sort of data it's learned from. There is no real what machine learning folks would call inductive bias. The way in which generalization happens from individual examples to a function, it's not something that we can really understand. And so it's very possible for it to have picked up something crazy, and then here is a manifestation of that. But at the same time, of course, these ML models are also extremely hard to interpret, unlike traditional software, where you could imagine doing debugging or program analysis. That is very difficult over here. And also, just how do we train this kind of model, that is a big, challenging question. And it turns out that in a lot of settings, you would have really unreliable training. You're going to remember all sorts of low-level stuff about the environment. The amount of data that you're going to need is going to be absolutely massive, which also doesn't necessarily bode well. And so what folks in this area of neurosymbolic programming, such as ourselves, what we have been advocating is that we should bring in symbolic knowledge represented using high-level programming abstractions as a way of countering these difficulties with contemporary deep learning. And there are two elements of this. One of them is that you're now thinking about representations of models, these functions that are being learned using machine learning. You're imagining that these are going to be represented as programs instead. And why not, right? Because ultimately, if you think of a neural network, it's a function, right? But if you think of a program written in a functional language, that's also a function. And so you could imagine that just like, we learn a neural network, we are going to now learn programs. And actually, that's what program synthesis has advocated for a long time. So that's the question of representations. And in particular, we are going to be interested in representations where you have a mix of these classical, symbolic sort of code, but you're also going to have neural modules. And the reason is that neural modules can represent things that are very difficult to represent using symbolic notations succinctly. And so we want to have the best of both worlds. And then also, the second part of this is that we are going to have learning algorithms that are going to bring together these continuous optimization techniques and sampling-based techniques that are typically used in machine learning with the sort of symbolic reasoning that we like to do in the PL world. And so the union of these two components is what we call neurosymbolic programming. And we actually recently wrote a survey about this. If you are interested, you could look at that. That will offer more details than what we can offer over here. So here's the outline of the tutorial. This is a pretty small audience, so we would like to keep this really informal. If you're confused about anything, just stop us. And if that means that we can't get through some of the content, that's totally okay. But here's what we have in mind at this point. So we are going to start with an overview of just basic deep learning. This is kind of the Cliff Notes version. And then we are going to talk about neurosymbolic programming. We are going to give an overview of the main kinds of function representations and algorithms that are emerging in this world. And you'll see that there's something quite interesting that's coming out. There's a systematic taxonomy at this point of different kinds of models, different kinds of algorithms that you could have over here. So we're going to talk about that. And then we are going to do a deep dive into an application of these ideas. In particular, we are very motivated by the use of these ideas in the setting of AI for science, where you are using machine learning to accelerate scientific discovery. And this is a universe where you definitely want data-driven learning, because scientific investigation in the natural sciences is fundamentally empirical. But you also have prior knowledge that you can express in these sorts of rich symbolic notations. And then that will be, we are going to do a deep dive into that topic, and that will be our session 1. In session 2, we are going to go deeper into the algorithms, and we are going to explain some of the main categories of methods. We are going to go back to the scientific applications. Then we're going to talk a little bit about library learning and safe neurosymbolic learning, which are sort of more advanced topics. And that'll be it. Any questions at this point? Okay, so let's get on with it. So as mentioned, we are going to start with just a very basic overview of supervised deep learning. And just to recap, supervised learning is the situation where you have some data and the data items are labeled with the value of a target signal. So for example, you could have pictures on the internet as your data, as your X, and you have a Y, which is the, let's say, the labels of these pictures. And then you feed that to a model. And so what you want to do is you want to learn a function that given a particular X is going to predict the Y. And this function can be represented in a lot of different ways. You could imagine having a logistic regressor. You could imagine having a random forest, a decision tree. And in particular, of relevance to this talk, you could have neural networks. So then, what does machine learning, the overall pipeline, look like in this setting? So you're starting with some training data, and you have defined a loss function that tells you that, let's say that you have predicted an output, how far does this differ from the desired output on this input? And you specify a class of functions, a class of models that you are going to learn. And then you create this big optimization problem, which says that, find me a function such that the loss is minimized. And then you solve this optimization problem using your favorite algorithm, which in the deep learning context is stochastic gradient descent. And then hopefully you have done really well with this, and you've made some profit, whatever be your notion of profit. So that's the picture of machine learning. And in particular, in this tutorial, we are going to be focused on the learning algorithms and the class of models. So whereas in deep learning, the model classes are just parameterized functions, specifically neural networks. For us, it's going to be a broader space of functions represented using these programmatic notations. So think of a domain-specific language as the definition of a set of functions that you can select from. And in the learning algorithm, rather than just being this one algorithm of stochastic gradient descent, we are going to have algorithms that combine our favorite symbolic techniques and also stochastic gradient descent. So now let's talk a little bit about the model classes that we showed in the previous picture. So as mentioned, you could have a wide variety of those. So the most classic is something like linear models. You are just trying to fit a line or n-dimensional version thereof into a data set. And then you could, instead of a linear model, you could have a quadratic model, which would make that could increase the expressiveness of the models, and you could go for higher degree polynomials as well. Or you could increase complexity in a different way, where you have, instead of one line, you could have 2 lines. You could have 2 linear models, and together they could describe a nonlinear function. And so essentially, as you're increasing the model complexity, you are allowing yourself to fit the data more and more. Now, of course, there is the risk that you could fit the data too much, the training set too much, to the extent that you wouldn't generalize well when you see something new when you have deployed your model. Now, in this tutorial, again, our starting point is deep learning. So we are going to be focusing on these deep neural networks, which are nonlinear models. And at its simplest, so if you just think of a single neuron, what goes by the name of neuron in this world, is it's a function that looks like this. So you are taking in a bunch of inputs, which are real values. You're taking a linear combination of these inputs, and then you are passing the result of this linear combination through a nonlinear transformation, of some very specific forms, and then you are getting an output. Now, typically you're not going to use a single neuron. You're going to have a layer, which is basically a whole bunch of these neurons arranged that are operating in parallel. And so it's going to look something like this. And then, when you go from one layer to multiple layers, you're going to have a bunch of these layers stacked on top of each other. And the final output that you're getting from the last layer, that is going to be your ultimate output that you get from the neural net. Yeah?
These hidden features, do they come somehow also from the input, or are they just fixed? And
so you're starting from the input, right? The input is over here, and then the input is passed to the first layer.
Yeah, I mean the hidden feature up there, the hidden feature.
Oh yeah, so these are not directly coming from the inputs; they're coming indirectly through the application of previous layers. Yeah, and so there is this question of that I just said that there is a linear transformation here, but what are the weights of that linear transformation? So those are the parameters that you're trying to learn. Okay, but once you have learned, then you have a fixed set of these linear and nonlinear transformations, and then you're basically saying, I'm just going to take an input vector and apply the series of transformations to that. Okay, so why do all of this? Well, there are two big arguments. So one is that you have a lot of expressiveness over here. And so you can think of each of these layers as basically being a simple transformation that you are applying to the input. And then what's happening is that, let's say that you have started with a whole bunch of points, let's say that this purple and yellow are these two categories, and they are all mixed up together because your ultimate goal is to separate the purple and the yellow points. But at this point, you see that just if you try to fit a line or a quadratic function, it's not going to fit. But what you're doing in every layer of the neural network is that you are moving these points around in space using first a linear transformation, and then you are basically selecting some subset of that. And so once you have applied a whole bunch of these transformations, then these points just move around in space, and at the end you end up having these points clustered in a way that's more easily separable by something simple like a line or a plane, right? So essentially you can think of as you're going through the layers, as you're increasing the depth of the network, you are giving yourself more ability to express really complicated concepts. Even if you had started out with a really mixed up set of points, you are going to at the end get the ability to separate these sets of points. So this is very high level. If you want to get more, there are lots of resources online about why deep neural nets are so expressive. Okay, and then the second benefit is that unlike our classical program synthesis, where you're doing all of these combinatorial exploration of big discrete spaces, here you have a differentiable space, and that means that you can apply these highly scalable continuous optimization techniques. And in particular, the universal algorithm for deep learning is stochastic gradient descent. So what you're doing there is that you are just writing down a big differentiable function, and then you are essentially doing, you're computing the gradients, and you are adjusting the parameters of the function based on these gradients, and you're essentially going, down a hill, except in a very, very, very high dimensional space. And as we know from all of the reports in the media, this stuff actually scales. It often takes a very long amount of time and lots of machines, but you can get really good optima out of problems that have hundreds of billions of parameters. So that's a big benefit of deep learning. Now, all of this is great, right? Where does neurosymbolic programming come in? And here we again go back to these weaknesses that we talked about earlier, the opaqueness, the lack of interpretability, the brittleness potentially, the complexity of training, all of these problems we want to address using symbolic methods. So let's see what that looks like. How do we specifically use symbolic knowledge or code or programs in order to address some of the challenges that you see in deep learning? And so again, there are these two ideas. One is the use of neurosymbolic function representations, and the other is the use of neurosymbolic learning algorithms. And so let's just handle this one by one. So let's talk about neurosymbolic function representations. And here, you are building a bridge between these two different kinds of representations. So symbolic programs are, more human interpretable if written in a reasonable way. You can apply these sorts of verification techniques that we in the POPL community love. We can express, structured domain knowledge. They are data efficient because, you're typically not learning. And when we do learning, in our program synthesis way, then we don't need lots and lots of examples, right? Like when we synthesize flash fill programs, we are typically synthesizing from a very small number of examples. We are not, training on very large data sets. On the other hand, neural networks are, the algorithms for learning are scalable. They're very flexible. They can handle messy data. The simple input-output interface means it's easy to get started. So when do we need to bring these two things together? And so here's an example of that. This is an application from the space of control where we think that neurosymbolic methods have a lot of natural applications. So here, imagine that your goal is to control a car. And the way this car is set up is that you have this controller and it is interacting with this environment. And at each point of time, the car is taking an action. And as a result, the state of the environment is being updated, and you're also getting a reward out of this. Now, more technically, this is you can model this as a Markov decision process, which is the standard formulation that is used for policy learning, reinforcement learning, and so on. So symbolic code for tasks like this has been written for a very long time. Control engineers have written control code using these blocks like PID controllers for a very long time. And so in a PID controller, you have a simple function that takes the current state of the world, which for the car, in this case, it would be the values coming out of a bunch of sensors. And then you have a certain target velocity that, let's say, you want to get to over here. So let's say that you are reading the current velocity and you want to get to a target velocity. And there are these terms that have been derived, using deep domain knowledge that tell you what kind of actions to take in order to get closer to achieving this outcome. And again, there is a lot of theory over here that would tell you, that would give you guarantees for stability and so on. And this is what control engineers have been doing for ages before machine learning. And now, of course, you can go beyond just having a simple PID controller. You could imagine writing a more complicated function where you have these couple of different modes. So you are maybe, looking at what the where you are. So let's say that you're steering a car. You are looking at, are you aligned with the center of the axis, or are you kind of turned a little bit to the left or to the right? And then maybe you're taking different actions in the two cases. So, for example, if the car is aligned with the axis of the track, then you decide that you're going to, invoke a PID controller with a certain set of parameters that maybe tells you to accelerate. If the car is not aligned with the axis of the track, maybe you decide to, slow down, and that means you invoke a PID controller that has a different set of parameters. And this is just one program that you could imagine writing over here, right? So this is, again, the symbolic, programmatic, POPL, PLDI, control theory way of writing controllers. Now, what would be the machine learning way of writing a controller? Well, there you're going to learn a controller from data. And so here, now, instead of having this program which is the controller. Now you have a neural network, let's say, and you're exploring the environment by, for example, sampling trajectories and seeing what kind of rewards you get. Now, of course, in the real world, that's difficult. This assumes you're doing it in a simulator. But you're collecting the data somehow, and then you are learning a function from that data. So then, what would be the neurosymbolic way of doing this? Well, it could be a combination of both of these things. So imagine that instead of using just the neural network or just the symbolic program, you use a combination, a composition of these two things. And what could such a composition look like? Well, here's a very simple example. So here what you're doing is that you're taking a linear combination of the result that is coming out of the PID controller and the result that's coming out of a neural network. And that's it. That's the decision that you're making. Again, ultimately, here your goal is to make not a discrete decision, but take a continuous action, right? So you have a steering wheel. What is the angle at which to turn it? It's a continuous value. Let's say that you have, some gas pedal on which you're putting some force, how much force to put in. So these are all, continuous actions that you're taking. And so this thing type checks, right? You have something that has a continuous value coming out, a program, a symbolic program, and you have a neural network which also has a continuous value coming out. And you're taking the linear combination of these two things. Why would you want to do this? Well, the reason, intuitively, is that if we think of what the weakness of the symbolic controller is, it's that it is too inflexible. It is using this kind of one size, maybe not fits all, but fits a very large number of cases solution. And as a result, when you have some tricky maneuvers to do, it's not really doing anything fancy to perform those maneuvers. And as a result, having a little bit of extra flexibility that comes from data might really help. But on the other hand, with the neural network, the problem is that it's learning entirely from data. There are no real priors that are being exploited. And as a result, you have often very unreliable training, especially when you're trying to do these sorts of control tasks where you have to make when the function that you learn is applied again and again in this kind of a sequential way. So it turns out that in order to learn, you need a very large number of samples, which is often difficult in real world settings. For example, in this kind of application. So this linear combination idea, so if you have to phrase this in the terms of machine learning, so it's really the use of a program, a symbolic program, as a regularizer. You are adding this extra term in order to reduce the statistical variance in the learning process. And there is, again, theory for this, reduce the amount of, the number of samples that you need, the amount of data that you need in order to learn reliably. Yeah?
How do you determine the good value for lambda?
So there are strategies for doing this. It turns out that you can frame this as a game-solving problem where you are trying to find lambda and also the parameters at the same time, but there is this kind of the quantifiers alternate. There is a little bit of complexity to that, but basically there are strategies for doing that. Yeah?
So linearly mixing two things isn't always a good idea, right? Like, think about taking a left turn in a car. One strategy is you wait for the oncoming traffic to go by.
Yeah.
The other strategy is you go for it.
Sure.
Halfway, it leaves you stuck in the intersection.
Yeah. Yeah, so of course, what you're saying is that if the two functions give you widely differing outputs, then what are you going to do? Is this going to work well? No, in that case, it's not going to work well. For this to work, there is this assumption that you are essentially getting a reasonable prior from this from the program. So, and everything else that you're getting out of the machine learning component is going to basically add more flexibility to it, but it's not going to completely give something different. And if it does, then these guarantees don't hold anymore. Yeah?
Back to to that example, what do you mean by flexibility for the left turn? Is it how you do the left turn?
Yeah, so for example, to make this a little bit more real world, one of my collaborators, he used this kind of idea to control drones that are making very tricky physical maneuvers. So it turns out that if you are, like if your drone is, at a reasonable altitude, then all the normal equations of physics apply. But when you're very close to the ground, there are these kinds of boundary conditions that start coming up. That the friction doesn't work in the same way. The laws of physics kind of break down. And so for those cases, you want to use something different. That is not just based on prior knowledge, but based on just what you're observing in such situations. So that's where you're getting this kind of extra data-driven knowledge that cannot be naturally expressed symbolically. And so what you are now getting here is a combination of the two things. That ideally, what this is going to lead to is that if you train these two things together, in a normal circumstance, this component isn't going to add that much extra value. You're mostly going to stay close to what the symbolic code is outputting, but in certain cases, you're going to get a lot more contribution from that. So here's an example of this car situation. What this leads to. So basically, because you have this combination of the two things, what you end up getting is that even when you don't have too much data, even when you haven't trained too much, you still get kind of sort of reasonable behavior. Whereas if you were starting with a randomly initialized neural network, you are just starting with garbage, and then over time you are going from garbage to something more reasonable. So here's a visualization that my former student Abhinav, who's a faculty at Penn State now, he made. So on the left you have the card that is regularized. That means it has the symbolic component. And on the right you have the neural card. And you see that here pretty early on in the training process, that regularized card is still giving a reasonable behavior, whereas this neural card is not. And this is again, a demonstration that it doesn't have to be 0-1. It doesn't have to be all neural or all programmatic. You could combine these two things, and that way you have this kind of a smooth transition between the kind of code that we always have written and this kind of code in the brave new world of machine learning. And this idea, by the way, has been applied in other settings as well. So I was talking about these drones. So this kind of neurosymbolic function has been used to represent not decision-making or policies, as they're called in reinforcement learning, but models of the world. How does the world change over time? So the classical way of doing that would be to use these sorts of physics equations. And the details don't really matter. The point is that they are symbolic. But now you could imagine having these extra neural terms that are added on top of these classic physics models. And so you now have these neurosymbolic functions that are more expressive than your classical physics models, but that are, again, not that come with some amount of reliability. So this has been concretely instantiated in the setting of, for example, boundary conditions of drones. So that's the video of what I was talking about. Highly dynamic environments where robots are deployed, and this is a swarm of drones that are controlled using these kinds of methods. So there's a lot of cool stuff that you can do with these kinds of techniques, and these are cases where just raw machine learning, raw deep learning just doesn't work. These kinds of ideas are really absolutely essential.
So one thing you showed on the other slide with the car, this was a great animation, but how does it do against just the controller itself without any?
Yeah, so we have some numbers. The controller is going to be a lot slower. So if you measure, for example, how fast does the car complete a lap, that number is going to be a lot. So it's going to be a lot faster for the neurosymbolic car. Yeah.
You ever run into situations where having that regularization term in the beginning of training prevents it from ever reaching state action combinations that like are actually good? Like the training wheels prevent the neural net from doing its thing?
Yeah, absolutely, that can happen. So fundamentally what you're doing here is that you are preventing exploration beyond a point. Okay, so in life as well as in machine learning, there's this exploration exploitation trade-off. And so the problem with unbounded exploration is that you can get to, first of all, you need to explore a lot potentially, and you can get into very bad places. But also, if you contain the exploration too much, if you restrict it too much, then you can also lose out on good optima. And so here what we are saying is that we are using this kind of structured domain knowledge to do this kind of constraining. So it's not just something that we have pulled out of thin air. But at the same time, there are cases maybe where our understanding of the world is just not good enough, right? And so as a result, maybe we will lose out on certain good things. And that's a trade-off we kind of have to accept in this world. Yeah?
How would you compare this approach with, say, you simulate a bunch of training data using the symbolic model, and then you train this along with some other data to give you a nice initial weights on a neural net?
Right. So that's a good point. We would still count that as neurosymbolic, but it's a different approach than what we took over there. And I don't know that I can say off the top of my head that it will do better in this environment or worse. Did you have a question? Oh, sorry. Yeah?
So, is the contribution that the neurosymbolic part is giving inside, for the example for the boundary conditions, is that it's giving the network information that this is a boundary condition. So normally the network would not have enough data to maneuver correctly when it's on the ground like that, but the neurosymbolic part is sort of overriding such that it can.
So it's going to happen implicitly. So basically what's going to happen is that it's going to find that in those edge cases, the symbolic part of the model doesn't really give that much value. So it's going to correct its contribution using some extra output coming out of just the neural part. Whereas in the other places, it's not going to. But it's not going to be explicitly done. It's going to come out implicitly from the learning process.
So it relies more on the neural part in the edge cases.
Yeah. Yeah.
Is there anything special you can say about the explainability in neurosymbolic?
Yeah, so that was one of the big motivations over here all through. In the control setting, for example, you may be training in simulation, but ultimately you do want to take this controller and put it in a real widget. And at that point, relying on a neural network is very challenging. So we wanted to do really mostly symbolic. And a big motivation for that was that it's something that's auditable, explainable, debuggable, and so on. Okay, so the application that we will talk about the most in this tutorial, though, is not going to be control, but science. And I'm personally really, really excited about this. Actually, all three of us are, and a lot of people in this community. So the reason is, again, science is fundamentally about data-driven discovery. But at the same time, there is a lot of prior knowledge in science that we can leverage. And so it seems like a perfect setting for the application of these sorts of neurosymbolic techniques. And in particular, we have been collaborating with a group of behavioral neuroscientists for a while now. And the kinds of tasks that you want to solve here are you're given these trajectories of lab animals, specifically videos, and you want to learn behavioral models out of that. Now, of course, this doesn't have to be lab animals. You could generalize this to other kinds of agents in other settings, but this is our application setting. And so typically, the way this works is that you're starting with these video frames, and then you are doing some key point estimation, which is basically giving you this kind of a diagram. And then you are extracting these high-level features that are, for example, this is the tail, this is the head, and so on. And then your ultimate objective is to classify the kind of behavior that is going on at different points, and that's what you see over here. What these mice are doing. And so the kinds of key points that you have over here, they would be nose, left ear, right ear, and so on and so forth. So this is the concrete problem that we are going to work with. Now, there are folks in neuroscience who are actually hand labeling all of this stuff. They're looking at videos frame by frame, and they're labeling these videos with these different kinds of key point annotations and so on. And these are, graduate students in neuroscience. Now we want to reduce the amount of work. So one way in which neurosymbolic programming was applied to this setting is through this paradigm called task programming, which actually got a Best Student Paper Award at CVPR a couple of years back. So it's been accepted by the Vision folks. And so here, what you do is that you start by defining some, important attributes of these agents. So, for example, here, you are interested in these mice, so you define this feature that is the nose-to-nose distance between two mice. And then what you do is that you just write some programs. You write some programs that, for example, here what you're saying is that the distance between two noses of two mice is a little piece of code like this. Now, this is an extremely simple program. You could write something more complicated over here as well. And together, this allows you to basically, if you start with a trajectory where you have a sequence of these images, you are able to, and then, that has been turned into these sorts of XY features, which are, we are assuming, which are given. So these are the key points that are coming out of the key point estimator. Then you have these programs. So let's just focus on this program, and what this program gives you is, this function that is the nose-to-nose distance. And so now this knowledge, which, by the way, if you were just doing pure deep learning, this is not something that you would have available, right? Because there it's going to be just these uninterpretable vectors, and then transformations that are being applied to those vectors. But now we have this interpretable program in the middle, and now this is used to structure the process of deep learning. And so specifically, what's going on here is something like this. So one of the big challenges in deep learning is to learn these so-called representations, latent representations of data. And so what that means is that, one way to think about it is that can you compress the information that is there inside the input data, so for example, the trajectory that you're talking about here, into a very small number of bits in a way that is faithful to the semantic content of what's there in the data. And so, typically the way you do this is that you would have a neural network that's called an encoder, and then you have another neural network that's called a decoder. And your goal is that in this kind of model, is that you want to be able to spit back out the data that you started out from. So you start with this tau, you encode, you get this little compressed representation, you decode, you want to get back something that is faithful to the origin. And then if you can do that, then the Z is an important piece of information because it captures the essential semantic content that was there in the original. Now, typically this desire of having similarity between tau and tau hat, this is something you would write using a loss function, right? It's just a distance function. But now you are intuitively having a loss function that also includes this extra program. So for example, what you want to make sure, just as one of the objectives that you can set, it could be something like, so let's say that you have generated this tau hat, you are feeding it through this program, you're getting this lambda of tau hat, and now if you compare it with the lambda of tau, the original trajectory that you started out with, they should be similar. Because earlier you said that just tau and tau hat should be similar, but now you're saying, even if you apply this extra function, they should be similar. And there are So what you've done is that in this kind of deep learning process, you have introduced these extra losses that now depend on this prior knowledge, this programmatic knowledge that you have encoded. Yeah.
Can you instantiate this a little bit, like maybe on that mouse example? Is tau here video frames, or is it like the positions of those key points?
It's the key point. It's a trajectory defined at the level of the key points.
And the key points were found by learning or by graduate students?
The key points were found in this work. It was assumed that there is some graduate student work involved, but there is also some learning. But there are other efforts where you are actually trying to automate that process also using programmatic knowledge as well. But here, let's assume that you're starting out with this kind of trajectory at the level of key points. And so then, what all this architecture says is that, earlier, I was just in this world. This is the world of, representation learning that deep learning folks are excited about. But now you have this extra programmatic knowledge, and now you can use it in a number of different places to define, losses. So, for example, you want this latent representation, this compressed representation to be such that it can be decoded back into something that is also close to this bandit.
So when you're defining the loss function that compares tau and tau
hat.
Whatever the thing
Yeah. Tau chill, I guess. Not tau hat. I mean, it's
So would you be just using like the distances between the key points that were predicted over the time series or something?
Yeah, we'll be aggregating over the time points, and at each time point, you could define it in various ways, but one way to do that would be just looking at what is the Euclidean distance between the points in the old one and the points in the new one.
Okay, great.
So how does this help? Well, you could go and look at the stats programming paper, but it does help a lot. It turns out that the kind of representations that you learn, they are much more well factored, and we have been looking into ways in which this generalizes outside of the training distribution, meaning that if you look at videos that are somewhat different than what you started out with, maybe you have added an extra mouse, maybe you have changed some of the attributes of the mouse, you want things to be robust. And the use of this kind of programmatic knowledge does help with the robustness of the model. So as I said, there is a nice taxonomy of algorithms and models that are beginning to come out in this world. So I've already showed you an example of this sort of additive composition of symbolic functions and neural functions. There are also places where you are doing this kind of symbolic after neural. So you're starting out with an input, you're passing the input through some neural networks, then the results are being orchestrated using a symbolic function. There are cases where it's the opposite. You are starting with a symbolic function, and then you're taking its output, and then you have a neural net. So actually, the task programming example that we saw, that was kind of like that there were programs that were being used inside the learning process, but then the result of that program that was being fed to a neural network. And there are also cases where you have, branching. You have an even else, and you have symbolic along one branch and neural along another branch. So why would you want to do all of these things? So I already gave you two examples of the additive composition and this one. But say symbolic after neural, one motivation for that in prior work has been transfer learning. So meaning that you're a human, when you learn a new task, and then you are given after that another new task which should use this previous knowledge, you should be actually able to learn the second task more quickly than if you were starting from scratch. Let's make it common. So imagine that you know how to classify a digit. Like you look at this thing and you know that this is a 5. And now suppose somebody gives you a picture which has this bunch of digits, and they're asking you to sum up all of these digits. presumably, the knowledge that you have over here should help you with this new task. And if you were a functional programmer, the way you would possibly write a program that does something like this is that you're going to, use this classify digit as a module in a bigger function that you create, in which you are first doing some classification of the digits, and then you are mapping it to the whole, list of images, and then you are aggregating the results through an addition function. And that's the final output, the final sum. That's how you would do it, if you were writing code yourself. So the question that we asked in this work is that, can you somehow mimic a similar kind of thing in the neurosymbolic learning setting? And so the idea was that, imagine that you have this library of neural networks that you have been growing over time. And so here you have, let's say, a neural network that says, classify digit. So rather than trying to learn this new model from scratch, right, by starting with a randomly initialized neural network and just doing gradient descent, could we instead, build a modular program that has this classified digit as a component, right? And then it essentially searches over the space of programs, functional programs that are written using this module, and maybe also has some new fetch modules. And then it, eventually discovers a program that looks like this. And then, this function is already known. This function, it just learns from data at that point, after it has hypothesized a program shaped like this. So it's a different approach, right? So again, in pure classical deep learning, what you would do is that you would take the new task, you would be saying that here's a neural network, with randomly initialized parameters. I'm going to learn the weights of this neural network. And then I'm going to just go and do gradient descent. And then there are all these transfer learning approaches where you would start with a neural network for this, but then you're going to do some, hackery on top of that. You're going to stick in some new layers and so on and so forth. But here what we're saying is that, look, this is an algorithmic task. So there is a programmatic structure that I could hypothesize for this using symbolic techniques. And then, because this function happens to be differentiable, I could just learn, new modules inside this function, kind of given end-to-end data. Yeah.
Why would you learn addition?
Oh, that's just because, yeah, good point. That's because this result is not just a, traditional symbolic 1 or 2 or 3, it's not a traditional symbolic number. It's just a vector that's coming out of this neural network, right? So you have to do something like addition on those vectors, but you don't know that it is just the addition function that is there in Camel or Haskell or something like that.
Why not?
Because the input type of that addition function is just Camel integers.
Yeah, sorry, why does the classifier not say this is a time?
Oh, you could do that. I mean, if you're assuming that the output is just a discrete number, then sure. But a lot of the times it would be a probability vector. It would tell you that, I have the probability of this for the outcome 1, outcome 2, outcome 3, outcome 4. These are the probabilities of that. So you see, so if the outputs are more like, it's a probability distribution over the different kinds of results that can come out, then you would need to have a new function that you have to learn.
Yeah.
I mean, think about it. So if I have a digit picture, right?
Yeah. I mean, I still think 5 plus 5, even if that works with probability 3.
Okay, then don't. Yeah, by all means, don't learn it, right? If you have something available to you, then don't learn it. You can use that too. But the point I'm making is simply that, instead of just learning the whole thing end-to-end as a neural network, you could learn a modular composition of some OCaml library functions and some new neural networks and some of your existing library modules.
And, sorry.
Yeah.
Well, the task you're talking about here, is it that you are given this scribble picture and a label with the actual number?
Yeah, that's right. Yeah. Yeah, and here to simplify things, we have just assumed that it's been broken up into a list. because then you have to think about how to segment this into a list, but that's too much to get into. So we are just assuming here that we just have a list of those pictures. Yeah.
What if you wanted to get the distribution over possible sums? Is that something that would fall out as a
you could
simple tweak to this?
Yeah, so long as you have a differentiable thing. All this is saying is that you're just doing a program synthesis to search for architectures, and everything else, you are, and you're reusing modules just like you would in human written code. Harder question, I think, from that side. I don't know. Okay, maybe not. Okay, good. So just another thing. So this branching composition I talked about, that is often motivated by safety. And at a very high level, again, I'm just trying to give sort of the highest level intuition here. But imagine that you have a situation where you have, you're again doing something real world like driving a car. You have a symbolic controller for the car that is very safe, but also that is not very efficient. You have a neural network that is more, risky, but that can possibly perform better in terms of, your performance objective. So then, you could imagine a situation where you have an if-then-else branching composition where you are monitoring the state of the system as you are executing, and then for the most part you are using the neural network. But if you take an action, if you see an action from the neural network that is potentially risky, and the notion of risky, it can be made more precise. Basically, if it's not provably the case that this is a safe action, think of it that way, right? So if it's not provably the case that you're taking a safe action, then you just fall back on a verified controller, which is very safe, but again may not perform that well.
How do you know that an action is not safe?
So so basically, the way this is done in some of these papers is that you imagine that there is a worst case model of the environment, and then you do a proof with respect to that. And so you basically construct this, inductive invariant that will give you the safe region of behavior. And so basically, if you are exiting that, then that means that you are no longer in the provably safe region, and then you, fall back on something that is provably safe. Does that make sense? Yeah. And there is, there is more recent work which is actually trying to learn this environment model as well, and there's a lot of work there. But basically, the point is that again, you would think that just neural networks are that alone is very expressive. But here's an example of where branching compositions also make sense, right? So this picture that I showed of the different kinds of compositions. So these are all have motivations from this practical perspective. So so that's what these compositions are beginning to look like. There are potentially many others, combinations of these simple motifs, but so far these are the ones that have found that have been encountered in papers. Now, as for the algorithms, we are going to hear a lot more about this from Armando. But basically, the idea is that we want to combine gradient-based deep learning with symbolic optimization, as done in the program synthesis or the pre-statistical program synthesis literature. And these kinds of methods are still being used in state-of-the-art learning problems, and they have complementary advantages over the deep learning approaches. So, for example, this paper published just last year, or I guess 2 years ago at this point, Kevin Ellis and others. So here, the goal was to learn these morphophonological rules for human languages. So these are basically, rules that are connecting that are telling you how to start with a root, and then based on, for example, the tense, how to create the form of the root when you have changed the tense, when you have set the tense to something particular. Like here, the tense is past. So you're going from open to open. And then also, what does this sound like? So there are relationships between what is there at this sort of abstract symbolic level and the sounds that are actually produced. Linguists have studied these sorts of rules for a lot of languages, but the question here was, can I automatically synthesize these sorts of rules for human languages? Now the thing is, there's very limited amount of data in this case, but Kevin and others, they used SAT solvers to synthesize these rules, and this was used to learn rules for 70 data sets spanning 58 languages, and this is not something that you could do using grading-based learning. And so in the neurosymbolic program synthesis world, you have this bridge between these two categories of algorithms. You have algorithms for discrete program synthesis, like the use of heuristic search, solver-based search, deductive pruning, the use of version spaces, like was done in Flashfill, and all of the stuff from the machine learning world. Yeah.
2 slides before.
Yeah.
What was the symbolic aspect?
So it's ultimately you're trying to generate these rules that are telling you that if I have this root and this tense together, the outcome of the combination is this. So this is something that you can express symbolically as a root, and you can basically frame a search problem that I'm given this, universe of possible rules, and I want to find the ones that fit the data. Right? So this is a program synthesis problem in that sense. And then how do you solve it? That's where the solvers come in, because it's a discrete space. And you want to add something?
No, it is 2022.
Oh, okay. So it was last year. Okay, so let's not talk about program synthesis. Let's just make this concrete. So the deep learning picture, or the machine learning picture, was that I have data, I have learner, the learner gives me a function or a model out of the data. So now I have, in addition to the data, I also have a programming language. This is the DSL. And I could also actually have some additional constraints. And these could be all of the formal specifications that we love in the PL community. This would be safety constraints, robustness constraints, temporal logic constraints, all of that. And then what you're trying to do is you are trying to learn a function, but the function has to have a representation in this L, which is this domain-specific programming language. And my goal is to still optimize a certain objective. This is the, think of it as a loss function that you're trying to optimize. But now, number one, there's a syntactic requirement that F be expressible in the language. But also, if I have some extra constraints, I want F to satisfy those constraints as well. Okay? So basically, I'm bringing in syntactic structure and semantic constraints into machine learning. Now, this problem statement is extremely general. This encompasses all of what machine learning people are trying to do in the real world. Now, obviously, we can't solve this, in full generality, but it's a good thing to aspire to, because it also enables us to think about particular special cases, like what if this, I'm trying to learn modulo temporal logic specifications, or if I'm trying to learn modulo, pre-post conditions of a certain sort, or if I have DSLs that look like, branching compositions of some stuff. So this is a very general, worldview that can inform your process of learning. So here's a basic example of what such a DSL could look like. So for example, if you go back to this, this car controller example, where I had branching composition of a couple of PID controllers. So I could imagine that I have a program that is being learned, and the program can take some, it takes as its input a state, and it outputs an action. And then there are some algebraic operations that are available. There are some, branching compositions. There are maybe some parameterized functions that are already defined. And that's the search space you are defining. And then your goal is to go and figure out a program that meets that structure. And then in order for this to make sense, you need to have a notion of, what happens when you execute a program. So you're imagining that this is, given to you as an interpreter as well for any program, how to execute it. Andrew.
Yeah, so I was just thinking about the previous slide, you had this conditional, give your neurosymbolic program, which
Yeah.
conditionally chooses between using a network versus a program.
Mhm.
So why, I'm just trying to understand the benefits here. So why doesn't this sort of cause would the network kind of, well, I guess you're never going to let the network sort of work when that condition is
Yeah.
the other way.
Yeah,
In
exactly.
principle, it could maybe learn to do whatever
That has proven to be a bit tricky, but yeah, we can talk more offline about that. There are some methods that try to learn that condition, but basically as soon as you try to learn the condition, provable correctness is not possible. At that point, you have like statistical correctness.
Yeah, okay. I guess I was just wondering if maybe what would happen is that the non-network computation, sort of the traditional computation, would serve as an initial kind of bootstrapping process and then in principle, the condition could move so that it always becomes true, and then you always end up using the neural network. You see what I'm saying? Like,
yeah, so actually
switching effectively from one to the other.
Right, so the work that we actually did there, basically you're starting with a case where you're very conservative, and then progressively you're adding more and more neural flexibility, but modulo the invariant that you never do, you never violate it. There are algorithmic solutions you can think of that have that property, but at its very basic, the form of the program is such that you have this kind of a branching composition. Okay, so that's what the problem statement looks like. So what about, semantic constraints, safety constraints, liveness constraints, knock yourself out, right? All of this. Now, given such a DSL, the problem then becomes that you start with a loss function, you use a learning algorithm, which is a program synthesis procedure in this case. It gives you a neurosymbolic program. And then maybe you take that neurosymbolic program and do some downstream analysis, and then that might lead to a revision of the loss function, revision of the DSL, all of that is within scope. And just some observations about this, that if you didn't actually search for the structure of the program, you could still do something, right? That would be like you're fixing the symbolic architecture of the model, and you're just learning parameters. And this is something that has been done before. This idea of neurosymbolic learning actually is quite old. It goes back to the late 80s, and that's what people were doing back in the day. If you set the architecture as just a classical neural architecture, like a convolutional neural net architecture or a recurrent neural net architecture, then you just get standard issue deep learning. And finding this structure of the program is kind of analogous to what some ML folks do, which is searching over neural architectures. Here we are using this sort of high-level algorithmic knowledge in order to do that. And then in classical program synthesis, the parameters that are coming out of the neural net, those are not there. So you're really just focused on searching over the structure, the architecture. And so really what is going on here is that it's really combining the program synthesis perspective with the deep learning perspective. And in the next block, in the second session, Armando will tell you about some of the different strategies that we have here, algorithmic strategies that are emerging. So for example, neural guided search is where you are doing a classical search-based program synthesis, but you're guided by a neural network. Symbolically guided deep learning is one where you're bringing in symbolic knowledge to set up the loss functions, for example, of a deep learning process. The task programming work that I mentioned is an example of that. Distillation is one where you're learning a neural network and then you're synthesizing a program that mimics that neural network. So you're basically distilling the knowledge of the neural network into a program. Relaxation is the other way around. Component discovery is where you're going beyond trying to find a program that fits a goal, but you're actually discovering a new DSL. You are learning a new set of capabilities modeled as a DSL. And we are not going to go through this in the interest of time, but and also Armando is going to talk about that. But just to wrap up this segment of the tutorial, I wanted to give you here a very high-level overview of what all is going on here. And many of the ideas here build on work that was done in the 80s and 90s and so on. But now there is a it's a really great time to push on these ideas. And the reason is that there's been a lot of progress in the symbolic formal methods community over the last 20, 30 years. And of course, all the revolutionary advances in deep learning. We have new algorithms that can scale as a result of this. And there's also a big demand by domain experts. So, we're going to talk about this large National Science Foundation project that we have in this area. And there, we are interacting with scientists who are interested in these methods. And yeah, there's a lot of excitement. They don't want pure deep learning because they want the interpretability. They want to understand the world. Same thing applies in healthcare, in many control settings. And so there is a great area, a great amount of demand by experts. And so the question for us is, can we deliver? And we are making progress, and I hope that you're excited enough about all of this that you join us in that. And with that, I'll give it to Atharva. And
I think I'll just use the keyboard here.
Okay.
Okay, all right. Let me just orient myself.
About the application of science more.
Right. So Swarat basically gave everyone a high-level overview of neurosymbolic learning, and what I want to basically do in this section is to showcase how these algorithms are actually being leveraged to solve the real-world tasks that we have in the AI for science setting. So I'm basically dividing this up into two parts. We'll first basically go over a high-level overview. I'll just get everyone warmed up about the behavior analysis problem. And then I have a bunch of Google Colab notebooks where we'll go through basically hands-on exercise for this. So make sure you guys have a laptop, or if you guys have, make sure you guys have a laptop with a Google account, if possible. Okay, so the problem we're interested in over here is this problem of behavior analysis. And in general, we basically have a set of videos of organisms interacting, and our goal basically is to partition this set of frames into different behaviors. I'll call these set of behaviors observed behaviors, and they're basically useful for a lot of downstream scientific applications. And I'll talk about three specifically in the case of mice behaviors. So, for instance, behavioral neuroscientists will record the neural activity of these mice, and then they'll try to quantify the relationship between these observed behaviors and this neural activity. This is also useful in the pharmacological evaluation setting. So basically, like, experts are interested in how different drugs might affect mice behaviors, and we'll basically look at the observed behavior and see how different drugs affect how the mice are interacting. And finally, we've also seen biologists who will use these observed behaviors to study how variations in the strain of these mice basically affects the interaction between these mice. Now, in all these use cases, the central problem is something we call behavior quantification. So we're given a set of frames of mice interacting, and we basically want to know the behavior at each time step. Now, again, as Swarat mentioned, the pre-machine learning answer to this problem was having a scientist basically sit down and look through these videos and manually tag each individual frame. And I'm told this basically used to take about 100 hours of annotation for every 24 hours of recording. And they would basically have weeks of recording for doing a single paper. Now, our goal over here is to basically automate this process, or at least help scientists in this. And specifically, what we're going to do is we're going to leverage machine learning. And at the same time, we want to be able to use the pre-existing domain knowledge in this setting to add some additional structured bias. So how do we do that? This, again, is something that Swarat mentioned. We basically have a two-step pipeline. The first step is this key point estimation process. What we're doing is we're looking at each frame, and we're using a convolutional neural network which outputs an X and Y coordinate for each of these interesting points. These interesting points are called key points. And again, all the heavy lifting here is done by a neural network. Now, once we have these key points, we train the behavior classifiers on this more condensed representation. And the supervision signal here is a small bunch of behavior labels that we are basically asking an expert to provide us. Okay. So, oh yeah, okay. So
At least in this tutorial, training the key point estimator is out of scope. We don't have the GPU compute power necessary for that. But what we'll do is we'll just focus on the neurosymbolic programming part of this. And we already have this dataset called the POPL'23 dataset, where we've already done all of the manual pre-processing and the key point estimation, and basically presented this in a dataset. And at least for this tutorial or the hands-on component, our goal would be that to basically use neurosymbolic programming to learn this relationship between the pose, these key points, and the behavior that we're observing. Now, I'll go a little bit more in depth about the DSL we're using now. So specifically, okay, there is already a lot of domain knowledge for studying and analyzing these mice behaviors. Swarat mentioned one of these. I have 4 of these on the right-hand side over here. Now, overall, so what we're giving you are raw trajectories, that is these expert annotated behaviors in this, and then these behavior attributes. Okay, going through a couple of these behavior attributes. So we basically have features like the facing angle of the mice, the nose-to-nose distance, the nose-to-tail distance, the head-body angle, and all of these features have basically been used in previous papers by behavioral neuroscientists to study mice behaviors. And it basically is a good base for our DSL over here. So specifically, this is the first component of our DSL. We're going to have these feature selectors. The other component of our DSL will be temporal filters. So basically, behavior quantification is inherently what we call a temporal classification problem. And in general, looking at a window of past and future frames really helps basically predict what's going to happen at the current time step. Now, the only issue is that this introduces an additional layer of complexity because we now need a new way of aggregating the belief over all of these frames. And these temporal filters essentially what allow us to do this. So for instance, the filter you see over here will essentially give more weight to the middle part of the window that we're looking at and less weight to the external, to the outside edges. Okay, and finally, the last component in this DSL are function compositions. These functions are inherently composable, and yeah, so function compositions, addition, subtraction, multiplication, division, really work well here. Okay, going through a sample program in our DSL, I'll just put this program here. I'll give you guys a minute to just stare at this, but what we'll do is we'll run from the innermost terms to the outermost terms and just try to basically come up with an English description of what this program means. So specifically, okay, looking through the innermost section, nose-to-nose distance, nose-to-tail distance, these are the behavior attributes. These are given by a neuroscientist. The select function over here is just defining a linear classifier, and we'll use various optimization techniques to find the parameters of this linear, to find the weight and the bias of these selectors, basically. The OR function and this window average function. The OR function is just one of the ways in which we can compose these two selectors, and this window average is the temporal filters I was talking about. It's a very naive filter that will basically say, take 5 frames and aggregate the belief in these 5 frames, and that's going to be the behavior classification for that particular time step. So intuitively, the description of this program in English would be something along the lines of that the sniff behavior occurs with high probability when the nose-to-nose distance and the nose-to-tail distance is above a certain learned threshold. And this has to hold true for like 5 frames, basically. Now, this is a program I made up, but what we find is that when we actually try to do differentiable program synthesis here, which is what we're going to be working on the next session, we can actually find good programs that actually give us comparable accuracy to a fully neural baseline. So the red thing that you see over here is the F1 score, and in this case, it's like comparable. I can go into more details of what these graphs mean. Feel free to like just talk to me offline about this. I just want to run through this right now. But I think on a high level, what you see over here is that the programs that we're learning through the program learning aspect of this are much more interpretable. They have a much more clearly defined structure over the window, unlike the 1D ConvNet baseline that we have. And in the tutorial, we'll basically go through different techniques for basically interpreting what each of these, the program learning and the 1D ConvNet example, or like how behavior neuroscientists basically look at these things and try to like make sense of what the models have learned. Okay. So we've also been able to integrate like these programs, these learned programs, into an actual framework called the Mars Action Recognition System. So this is a framework that's used by behavioral neuroscientists to tag and to understand the underlying behavior over here. So what you see in orange here is what the human being is labeling. What you see in green on the left-hand side is the program output. And on the right-hand side over here are basically the belief and the actual underlying program that we're using for getting these labels over there. Just wanted to showcase this as like how this is actually being deployed and actually being used in behavioral neuroscience labs. Okay, that was the relevant information and just like a general Cliff Notes version of the behavioral neuroscience setting.
Just walk through the code because we don't have time for people to actually do that.
Great. Okay, let me see how I can. I'm sorry, I don't know how to use a MacBook, so. So let's see. Yep. You'll have to open up a. You can just open up. Okay, sounds good. This is good. Yeah. This is a perfect page. If you can just put this on the next screen.
Okay, but you can't see.
It's okay. I'll figure it out. Okay, I see myself. All right. Okay. I'm wondering if I can just walk through the notebooks directly. So this was meant to be done in Google Colab. I'm assuming people aren't doing this, so that's all right. The way I'd segmented this was basically first looking at the actual data exploration part of this. So we were going to be looking through what the mice key points mean, how they're actually segmented, and we basically had some exercises for looking through, seeing how these like are actually plotted, and basically trying to understand or try to form an intuitive understanding of what it means for different behaviors to happen. In this case, we were only looking at investigation versus no investigation. So we basically had binary labels. So you either had to classify whether the mice was interested in the other mouse or not. And the essential goal over here that we had was that like what we find is that like when mice are interacting, they're usually very close to each other, which basically leads us to thinking about, in some sense, a good feature for how to classify how two mice might behave when they're like investigating. And the idea here was that when the distance between these two mice is small, then that's a good, very simple symbolic program in some sense for figuring out if if the mice were again interacting or not. We had this neural network based example, which was this 1D ConvNet, and we basically had some way of training through this. And basically the idea was that like we would have done this, we would have plotted these, and we would have found that underneath the hood, like the only way of interpreting these neural networks is to see how they perform on a test set, and then try to like basically form correlations in some sense after you've trained them to see like that, to see like how they're performing. So in all these cases, also like what we see is that like when the class label is predicted 1, like mice are basically usually very close together. In some cases they're not, but that's just because the accuracy of these models is kind of stochastic. Then we had this program optimization section where we basically had this language, this DSL of how to reason about programs in this, how to reason about like behavior classification programs. And in the same way, we ran through a couple of programs. We basically had a module where you could input a particular program in this DSL and actually to train it and actually get an accuracy number to see how that program actually performs. And the hands-on component of this tutorial was for everyone to like basically go through and like try to like use their own programs in the setting, maybe try to change some configuration parameters. And the visualization component of this was basically to see how like behavioral neuroscientists would look at 1D ConvNets and would look at these programs. So for these 1D ConvNets, what we usually do is we look at the channel activation for each of the features that we had. And based on that, we tried to posit some relationship between how how the mice might be interacting and how each feature might be useful for different things. And then in the program analysis, sort of like setting this neurosymbolic programming setting, it's much easier. We can just print the program. And that basically tells us, it gives us a much more interpretable way of expressing these same programs, while at the same time giving us actual parameters that we can plot and we can actually use in like something like a normal Python program for doing this sort of evaluation. I think that's overall everything that was in this first part. Notebook 2 and Notebook 3
are all available for you to play with. Of course, it's not doable, online during a tutorial like this, but it's all there. If you're interested, just send us an email, and we'll also post the links in the and the slides in the webpage for the tutorial test. And in the second part of this second session, we are going to come back to this, and we'll actually see how some of the program synthesis methods play with these notebooks. And this is all real stuff. People in neuroscience labs are using all of these methods at this point.
Okay, any questions that you think we can answer? Okay. Cool.
Okay, so we'll then see you for session 2.
All right, so welcome back, everyone, and I hope you had a good break. And we're getting ready for the second half of our tutorial. And so the plan for the second half is to talk a little bit more in detail about algorithms for neurosymbolic program synthesis. And so we're going to do some of that, and then we're going to do a little bit more of a deep dive, and then we'll have even more fun stuff. So to start, before we've already been talking a little bit about these neurosymbolic programming problem, where the goal is you have some data, you have a programming language, you have additional constraints, and what you're trying to do is you're trying to learn a neurosymbolic model, where your goal is to discover both its structure, which we like to represent using this parameter alpha, that this is generally not a continuous parameter, but rather it's a set of discrete choices about the structure of the code, and this parameter theta that determines the continuous choices that you have within that model. And these are generally going to be parameters to some kind of neural network, although we use that term very loosely to refer really to just any parametric continuous function that you have within your code. And so what we're looking for is to find essentially the program, the combination of parameters that optimizes this expression. So you want to minimize both the loss that you get from both of these parameters, and you can think of these loss as representing the semantic constraints. These are the constraints about how this program is going to actually behave or how it's going to perform when you run it on some test inputs. It might also include some, it's usually going to be around data and how it behaves in particular scenarios. But then you also have some penalty that comes from just the structure of the program. We want to use this term to represent, for example, priors over the structure of programs. Knowing nothing about what your program is trying to do, you can still tell that certain structures are going to be less likely to be right than other structures. For example, one of the things that we always are careful with in the program synthesis context is you want to avoid programs that just have a bunch of branches specific to every input that you have seen, right? And how do you avoid getting just a giant if program? Well, part of how you avoid it is by having a penalty for having those kinds of functions. And so our goal here is to have learning algorithms that are able to take fairly open-ended domain-specific languages, fairly open-ended learning objectives, and from that, get a program that satisfies everything that you want. Now, as we have been working in this field, one of the things that we have identified is that there are actually many different approaches to combining deep learning and more traditional program synthesis or more traditional techniques coming from the PL world. And so, for example, one approach that has proven to be quite powerful and that is becoming very popular in the field these days is this approach of neural guided search. Now, what do we mean by neural guided search? The idea is that you're searching these discrete space of program structures guided by a neural network. We're trying to leverage the ability of neural networks to learn conditional distributions over these very complex objects. In this case, the object is just a program, and the conditional part comes from the fact that this is conditioned on the goal. Given the goal, you want to find a distribution of the programs that are likely to satisfy that goal. And in that way, you want to have a very targeted search. Another really powerful idea is what we call symbolically guided deep learning. Here, the idea is that at the end of the day, you're actually just going to be generating a neural network. So in some sense, you might say, well, isn't that just deep learning? But the idea is that as you are training that neural network, you're relying on knowledge encoded as programs, or more generally, knowledge encoded symbolically to guide the learning process. And this can take many forms. This can take the form of additional penalty terms, for example, that you add to your neural network to ensure that it generalizes. Or it might take the form of data augmentation, for example, where you leverage symbolic knowledge about your problem in order to generate more data. There's another really interesting domain approach that is referred to as distillation. The idea is you learn a neural network using traditional deep learning techniques, and then from that neural network, you extract a more symbolic representation, something that looks like a program. Now, when we talk about this to machine learning audiences, the obvious question that comes out is, why? Why in the world would you want to do that? You already have this neural network, you already learned what you were trying to learn. Why would anybody want something that looks like a program? Now, of course, we are PL people, we know better. And in particular, we know that there's a lot of benefit to having a representation of the thing that you're trying to learn as a program. For one, we have an entire toolkit of program analysis and program reasoning techniques that we can bring to bear on these representations to do things like verification, for example, that are much harder to do in these representations. The other thing that we can do is in that process of going from this to this, we can also incorporate a fair amount of domain knowledge in the form of the domain-specific language that you're using in order to represent your program in a way that, even though this representation is simpler, it might end up generalizing better than these representations, right? And in fact, one of the case studies that Swarat talked about a little bit earlier, in fact, follows this paradigm. The other approach is relaxation, where what you're trying to do is take something that starts out as a program and you want to relax some aspects of that to be neural networks. That might be, for example, a way to get a program that almost works, or that works reasonably well, but not as well as it could, and then to get it to adapt its behavior, to deal with corner cases that the program version might not be able to deal with. And finally, one paradigm that we're especially excited about is the paradigm of component discovery, where there is an interplay between symbolic and neural reasoning in order to extract reusable knowledge from your corpus in the form of symbolic components that summarize particular computational patterns that appear in your domain. And so over the course of the rest of this hour and a half, we're going to talk a little bit about some of these paradigms and a little bit about some of the algorithms that go into making some of these things work. Any questions so far? So let's start with neural guided search. So as I said before, this is a paradigm that is becoming quite popular in the field. And at a high level, the idea is something like this. So you can think of this process of building a program as exploring a search space where every state in this space corresponds to a partially completed program. And you have some actions available to you that correspond to choosing how to extend this program so that you get another program that is a little bit more complete. And so, for example, if you're generating programs one instruction at a time, so one node might correspond to some program that has some instructions, and then you get to choose what action to take, what extra instruction to add to your program. And so now you're going to have a new program that has one more instruction than you had before. Or one strategy that is very common in the program synthesis world is the strategy of top-down enumeration of programs, where your states correspond to programs with holes, programs where some parts of the program have not been fully fleshed out, and where an action corresponds to taking one of those unknowns, one of those placeholders, and fleshing it out, adding more detail about what this might be. And this might include replacing, for example, this hole with a variable, or it might include replacing a hole with another construction that itself might have holes, right? Maybe another function where now its arguments are holes. But in this way, what we are dealing with is still fits into the same paradigm of we have these states, we have these actions that we can take, and what we're looking for is what is the sequence of actions that is going to get us to the goal. Now, in a lot of the work from the programming languages community that was looking to do this, the name of the game was, how do we prune this space? How do we leverage our knowledge of program semantics, our knowledge of types, in order to prove that just some of these partial programs just are hopeless? There's no possible completion that can get us to the end. And that's very powerful, and that can take us pretty far. But the thing that, and in fact, type-directed enumeration is an extremely strong way of pruning the search space and achieving very, very significant speedups when we're searching these spaces, right? So we can look at each one of these partial programs. We can look at what are the types of everything involved, and as soon as we find something that doesn't type check, we can just kill that that branch. And there have been some experiments, for example, showing just the dramatic reduction in the size of the search space once you're eliminating all of these programs that don't type check. And the reason is type checking is very, very powerful because you can tell that something is not going to type check, even if it's still very incomplete, right? We're all familiar with this experience of, for example, using an IDE, and you get this red squiggly that says, hey, you have a type error here, even while your program still has a big chunk of it that you haven't written, right? From the point of view of a synthesizer, that means that that entire exponential space of possible completions to that program now disappears because you were able to rule it out early. But if we have a learning available to us, then we can do even better. For example, what if we actually use, in this case, the neural network to map from a description of the task together with the current state of the search and use that to predict what are the most likely actions, the actions where that are most likely to lead us to the goal, to lead us to something that corresponds to that, that satisfies that task. And so if we have something like this, we can actually do just a greedy search. We can just, at every node, we can ask the neural network, what are the probabilities for each one of the possible successors of this node, and just constantly pick the most likely next step. It turns out that in order for that to work, you need a neural network that is really, really, really good at making those predictions, right? And oftentimes the neural network can do a reasonably good job of saying, like, this is more likely than this, but likelihood, when we're searching for programs, it's not enough to find a program that is 90% correct or 99% correct. It is one of the features of programs that a single token might be the difference between a program that does exactly what you want and a program that maybe doesn't even compile, or a program that compiles but is wrong in every single answer. Or even worse, a program that looks like it works, except for some corner cases where it does completely the wrong thing and might even do something dangerous or undesirable. So can we do a little bit better? And in particular, can we combine the benefits of having these oracle that can tell us what things are more likely and what things are less likely with other sources of information? For example, one of the things that you often do in this kind of search is, instead of just greedily following the most likely solution, you keep track of the k most likely sequences. So you use these probabilities that you're getting at every step in order to keep track of what are the k most likely programs according to this network. And so now you have not just one program that may be right or might be wrong, but a small set of programs on which now you can apply other forms of reasoning in order to determine which of those programs is actually doing the thing that you want. Now, why would this work? So first of all, one of the things that is very essential for this to work is that you need to have some kind of corpus, some source of related synthesis tasks. You can think of these. This is now an approach where you can no longer say, well, here's my synthesizer, and I just finished writing it, and now I'm just going to go and try it out in all of these different problems. Now you have to train your synthesizer. You need to have a collection of related programs that you can use to do this. But if you have that, then you can take each one of your synthesis tasks. For each task, you might have a collection of input-output examples or other forms of specification. This is actually not limited to synthesis from input-output examples. You might have a program that tells you what program corresponds to this, and you can use that to train your model that is going to learn how to produce and how to prioritize the programs that look like the programs in its corpus. Now, there has been a lot of work looking at different representations for these programs, and there has been a lot of work trying to look at more clever representations that are more like the kind of representations that we have been used to. A lot of that work has been overshadowed by the tremendous progress in just sequence-to-sequence models. So that today, almost any model that tries to deal with data structures that are not sequences is at an initial disadvantage that somehow you have to make up. And so today, most people actually rely, when they do these kind of synthesis, they rely on these sequence-to-sequence models, the same kind of models that are used for things like question and answering, for language translation, even for things like completion, in order to just generate these programs, one token at a time, rather than using more structured representations. So essentially the way these models look like is that you have an input sequence that is translated by an initial network into a large set of feature vectors that encode all the information from this input sequence, and that can then be decoded into an output sequence. And today, the state of the art is really to use transformers. These are these very powerful, large-scale models that have been found to do a very, very good job at encoding sequences and identifying the relevant information from the input sequence and translating that to the output sequence. The first system to actually do this was called RobustFill. It's from 2017, and it was focused on this domain of text manipulations. The name is comes from the fact that it was essentially a neural version of the FlashFill work that was first published in POPL already more than a decade ago. But the idea was exactly to use these sequence-to-sequence models in order to do this translation, just like you might translate from English to Spanish. In this case, you're translating from examples to programs. And again, taking advantage of the fact that you don't just query for one program, you can query for a collection of programs that then you can actually run on your examples and filter out any programs that don't actually give you the right answer for the examples you have. And so you can, this actually works pretty well for these kind of text translation problems. Now, you might have heard about something called AlphaCode. It made a lot of noise last summer on the basis of actually being able to solve programming challenges from these programming competition problems, right? It's a very, in some ways, it's actually doing something very, very similar to what RobustFill is doing, except in this case, this was done with a very, very large transformer, and it used something along the lines of 1024 TPUs running over the course of a month in order to train the model. So it was really trained at just a completely different scale compared to the original RobustFill work, but the actual strategy was still very, very similar. You still have a model that is trained to map from a specification to an implementation, or in this case, the specification corresponds to the natural language text. And you query the model for tens of thousands, in this case, tens of thousands of examples that you then filter to weed out any example that does not actually match the test cases. And one of the interesting things about this work is that even though you have this huge neural network that was trained on over a very long amount of time, the success rate of these large set of programs is actually very, very small, and you really need to query to get samples with tens of thousands of programs before you will actually get programs that satisfy the specification. Now, a lot of these kind of strategies rely on having this corpus with specifications mapped to programs. And so this is a very powerful paradigm, but it also has some limitations. For one, your corpus has to have both things. It has to have specifications and it has to have programs. By contrast, another downside of this approach is that you're training the neural network to give you exactly the program in your corpus. Now, we know that you can have many different programs that look different, but that behave exactly the same, right? So this goal of exactly matching the program in the training set is not necessarily the matching what you actually want, which is not so much the exact program, but a correct program, any correct program. And so there's also been a lot of work around a different paradigm to learning based on reinforcement learning. So rather than having a corpus where you say, here's my specification, here's my program, you can have a specification, you can have the goals defined in terms of an environment that produces a set of rewards. So at every point in the search, your goal is simply to look at the current state, issue the next action, which in this case, in the case of synthesis, might be give me the next instruction or give me the next update to the program. But rather than having this predefined goal of we need to produce this exact program, we're going to evaluate it based on an environment that is able to tell us, have we gotten the right answer or are we getting wrong answers? And so to give you an example of what this looks like, this was from a paper that was led by Kevin Ellis. I was also part of this paper a few years ago, where it's using these reinforcement learning type of approach to train a neural network. And one of the things that is interesting here is that your neural network was actually trained to not even look at the program that you have generated so far, but instead look at what does this program compute? What has this program computed so far? The idea being that if you have the state that the program has computed so far, you don't actually care what the program looked like. You might have many different ways of writing that program, but it doesn't really matter. What matters is what has it actually computed? And so you can have some initial state. For example, in this case, we're looking at a drawing domain. And so you have some initial state, it's just a blank canvas. And then the neural network issues an instruction. It says, well, if you want to get here, let's draw a rectangle. Now you can feed that instruction through an interpreter. So the interpreter is now in the loop, collaborating with the neural network, so that the neural network doesn't have to look at that program and internally figure out what that program is going to compute. Why would we want the network to do that when we have interpreters that can do that for you in a completely precise way, right? So now the neural network just gets to see, well, here's the new state, here's the goal, then what if we do this, right? So now we have a new state. We have two new things that we can draw. What are we going to do with those? Well, again, this is the new state. You can go to the neural network. The neural network can tell you, oh, the next instruction should subtract expression 1 from expression 2. So now we have a new state, right? So at every point, the neural network is not trying to make this global prediction about what's happened. It's just trying to make this local decision based on being able to see the state as computed up to this point by a normal run-of-the-mill interpreter. Now, another aspect of this is that, again, the neural network is usually going to give you a distribution, probabilities over the different operations that you might take. And so rather than just taking the highest probability thing, what we want is we want to explore these search tree, guided, yes, by the probabilities given by the policy, but also guided by what is called in this field a value function, a function that is able to look at each one of these programs that you have generated so far that is in your wavefront and tell you, you know what, this program looks very promising. It looks like the kind of program that you might be able to extend to produce a solution, whereas this program really looks like it's gone off tangent and is not actually going to get to the right place. And so we can train both this policy and this value function together to give us a solution. Now, one of the things that is really interesting is that, in this setup, we can just train this neural network. And as long as it does a reasonable enough job at saying, this looks like a better candidate than this, it's actually going to help you find a solution faster. But if you can get something better, if you can have something more rigorous that really tells you, like, this is the estimated cost to go. If you're at this state, this is going to be the cost to get to the goal. right? And if you can put a bound on that cost to go, now all of a sudden, this is no longer just a way of prioritizing, oh, I'm going to look at this first and I'm going to look at this second. But now it's something that you can use to really rigorously prune that search space. Now you might think, well, yes, that's great, but that's not something neural networks are good for, right? Giving us really strong bounds on things. But what if we could do that, right? So for example, right now, if we have this value function, it's really not only once we get a complete program that we can really say for sure, like, yes, this program was correct, or no, this program was wrong. But one of the big insights coming from actually from Swarat's group was that you can actually get some pretty strong estimates, upper bounds of these costs to go by leveraging neural networks along the way. Now, this is a little bit different from what we've talked about so far, in that this is not about training a neural network ahead of time to learn how to run, but rather this is about using learning in the loop as you are exploring in order to give you some of these estimates. Now, what's the idea? The idea is, let's say you have a program like this, and this program has these holes. Now, what if you use a neural network to fill that hole, right? And you train the neural network to fill that hole. You find the best parameters for that neural network to fill that hole. So you're doing training in the loop right here during search over the space. Now, this might look expensive, but here's the idea. Neural networks are extremely expressive, right? Very, very expressive, potentially much more expressive than the restricted domain-specific language that you're using to build your program. What that means is that the neural network can act as an oracle that over-approximates the behavior of the actual piece of code, even of the best piece of code that you can use to fill that hole, right? So if the set of neural models is a strict superset of the set of neurosymbolic models, right, of models that now have all the strictures of these of having to adhere to this program structure, then what it means is that you can actually use that to get an upper bound on how good of an approximation you can get if you try filling that hole and you try completing that program, right? Because whatever concrete function that you plug in there is potentially not going to do as good of a job at approximating that behavior as the neural network that is trained to try to approximate that behavior. Now, there's all sorts of assumptions required for that to be true, but the question is, can we make this work in practice, and can we make this work well enough that it actually serves as a strong basis for guiding the search? And I'm running out of time here, but so I'm just going to jump to the punchline to say that yes, you can. You can actually train these neural networks to indeed do a good enough job at approximating the best possible program that can fill that hole, that you can look at how the program with that neural network behaves and say, yeah, that program is actually, that branch of the search tree actually is promising. I can put in a neural network there and approximate the behavior well enough that it gives me an incentive to keep trying to complete that program. Or by contrast, that you find that no, even with the best neural network plugged in there, I cannot do a good job with this program, because there's something already wrong with the code that I've already written. That it doesn't matter how good the thing that I use to plug in the holes, it's not going to be good enough. And so in this way, you can prune the search and actually get to a really good solution much faster than with many alternative search problems. And so with that, I'm going to give the floor to Atharva to tell us a little bit more about the case study that we've been talking about so far.
Right. So going through the code base may not be a good idea here, but what I'm just going to do is go through the overview of what we were trying to do and like just look at the code structure for the next two notebooks. And I'm assuming we can all basically look at this in our own time to figure out and like actually play around with this. For the next two notebooks, the general idea was that in the first one, we would explore how enumeration performs in a couple of different DSLs for this, again, for this problem of behavior quantification. And so we basically had three DSLs. There was this base DSL, which was just the selective functions we were looking at in the last session. There was a modulate filter DSL, which was actually adding in more temporal filters and trying to see that when we start adding extra control in basically how we aggregate on the temporal dimension, we can actually get much better performance. And as a third DSL, we had a neurosymbolic DSL, where we would actually allow neural networks as the terminal nodes of the programs we were looking at. And in all these cases, we find that going much more, allowing more expressive power basically allows us to like perform much better. And yeah, so this particular visualization chart basically becomes very important when we talk about comparing enumeration and NEAR. Armando basically talked a little bit about this, but basically the idea is that we have runtime on the x-axis and we have the f function on the y-axis. And in general, being higher up and to the left is much better. I think in that graph it was lower and to the left. But in the sense, like what we would usually see would be that having better DSLs basically leads to much better accuracy, and also allows us to get to a much better solution in lesser amount of time. Okay. And finally, like in an open-ended exercise, we basically wanted to implement our own temporal filters. So this is a symmetric filter that we provided, but it turns out that having these asymmetric filters and allowing for more parameters in some sense in the temporal domain actually helps the performance a lot. The third notebook that we had was actually going over NEAR, which is what Armando just introduced a second ago. And in this case, we had two DSLs. There was this base DSL of just temporal of just the filters, and there was this model filter-based DSL. And again, what we basically find is the same conclusion that the model filter DSL basically gets us much better accuracy than the base DSL. And if you actually try to plot this alongside with the DSL, alongside with the other enumeration techniques, we find that these are actually much more on the left-hand side compared to just enumeration directly, which actually just validates the idea that NEAR performs much better than enumeration, and it's a much better search procedure. And then there was some open-end exploration where we basically wanted to see how we can improve upon performance, and it turns out that there are 3 or 4 very simple ways in which the performance actually increases a lot. So for instance, you could just modify the heuristic architecture. So instead of using a two-layered network to guide the search, if you just use a 3-layered network to guide the search, the performance improves a lot. There were also ways of basically having different search algorithms. So instead of using NEAR plus A star, we could also just use NEAR plus iterative bounded depth, depth first search. And also, just to see how this performs on, instead of just having a binary classification problem, which was the investigation versus no investigation, behavioral scientists are also interested in a lot more different behaviors. For instance, mounting, sniffing, mounting different body parts, etc., etc. And we actually have code for training and seeing different programs and how they perform in all of these behaviors. This is just some details about the internals and like how they can be used to, how we can basically modify up the code base to like actually allow us to add more heuristics and add more DSL functions. And yeah, this was just like, the idea over here was just to like go through the notebooks and like try to see if you can modify a couple of things and see the effect of basically very simple changes and how it basically increases performance a lot. Yeah, with that, I think we're not going through the code base. I'm not sure if we have enough time for that. But I guess like you can continue on with the next part of this, which is the library learning component.
We do encourage you after the tutorial to actually take a look at those notebooks. because a lot of things that during the presentation might feel a little bit hand-wavy on the algorithms, once you actually play with them, you can really get a good feel for exactly what these algorithms look like and what they're doing. Yes?
Where can we find the links for these?
Yeah, so we're going to put this up on the page, but if you just go back, so it's just bit.ly. Yeah, and the great thing is that it's all on Colab, so you can go there and run machine learning and all of that. The backend GPUs will take care of that.
So we've talked so far about this idea of neural guided search and how we can use the neural network to help discover a piece of code. And in general, that there's a limit to how big of a program you can generate that way, right? Every time you issue another token, there's some probability that you're making a mistake. And the more tokens you need to issue, the higher the probability that one of them is going to be wrong, right? And so the bigger programs you're trying to learn, the harder it's going to get. And even very, very large systems like this AlphaCode, right? You're generating on the order of hundreds of lines of code, right? But one of the interesting questions is, what if you want to learn more, right? What if you want to build more? And the way programmers write bigger programs is through abstraction, right? By encapsulating concepts into functions that you can reuse, so that at no time do you really have to reason about a massive piece of code all at once. You're building these abstractions that then you can reuse in different contexts. And so one of the really interesting questions for us was, can you actually mimic that process as part of these neurosymbolic learning process? Essentially go from a collection of goals that you're trying to reach to produce the tools that the synthesizer is going to be able to use in order to achieve those goals, in case you were wondering about the little visual language here. So how might this work? So the idea is, let's say you care about list manipulation programs. And let's say that you start with a collection of primitives, low-level primitives that you can use to write these programs. And so in the beginning, you might not be able to solve very many of these problems. You can train a neural network to do neural guided search, or you can use a very, very fast symbolic enumeration technique, use types to prune the search space, and you're going to be able to solve some fraction of these problems. But the idea is that some of these problems are just too hard to solve in terms of this base language. The program that you need in order to do this is just too large to find. But the idea is that you can look at the programs that you were able to solve and try to identify common structures, common computational patterns that when you encapsulate them into a function, now you have this new component that can help you solve more problems, find more programs. And so, for example, you can start with the simple primitives and discover filter. And once you have filter, you might be able to now discover maximum, for example. And from that, you might be able to discover, for example, the nth largest element in a list, right? And you can start stacking these concepts on top of each other so that once you have a rich enough library, you can actually discover a program which, when written in terms of this library, is actually a fairly small program. But if you were to write it in terms of the original low-level primitives, you would find that it is a fairly large program, one that is much larger than what even a more sophisticated neural guided search might be able to find in a reasonable amount of time. And so the question is, how can we discover these components, and what does PL have that it can bring to the table? So we had this paper back in, what was it, 2021, where it's a system called Dreamcoder. And the reason is that it's building on these wake-sleep metaphor that is actually quite common in the AI literature, where during the wake cycle, the idea is that you're learning problems. You're solving as many program problems as you can. But then you have the sleep phase, where the idea is to consolidate all this knowledge and all this expertise that you acquired as you were waking up. And you want to consolidate that expertise and discover new symbolic representations for this expertise that are going to allow you to then deploy these more effectively during the next wake cycle. And the sleep phase is divided into two steps. So one is the abstraction sleep, where the goal is to improve your library, discover new building blocks by looking at all the programs that you've generated so far. But then you run into a problem, which is that as your library grows larger, yes, the program that you're looking for is now easier to write. It's more concise, but the branching factor in your search also grows, right? Now, at every step, you have more decisions that you can make. You have more primitives that you can choose to use. And so how do you avoid that? Well, you avoid that by being able to search in a very targeted way. And the way you search in a very targeted way is by building this recognition model that learns to recognize, oh, this kind of problem looks like the kind of problem that needs this and this and this component. And in order to train that, we essentially have this dreaming phase where the system is essentially hallucinating these different problems and using those to learn correlations between features in the inputs and outputs, with features, especially in the outputs, with what kind of components are used, right? So for example, if you see a lot of repetition in the output, you know that there's probably a loop somewhere in your program. That sort of relationship is what you want to discover. And we've actually applied this to a number of domains, ranging from this kind of list manipulation programs all the way to things like symbolic regression and some very classical AI domains like tower building and drawing domains with logo graphics. So, just to show at the high level what the algorithm looks like. So you have this waking phase where you have your library, you have your tasks, and for every task, you're using the recognition model to help guide the search for a program written in terms of that library that solves your problem. And you want to solve as many tasks as you possibly can within a budget. And so essentially what you're looking for is you're looking for the best program that that maximizes the probability that this is the right program given this task description and given this language, but conditioned on the recognition model, saying, yes, this is an appropriate program for this input. And then you have the abstraction phase, where you're trying to discover these components from a number of different programs. And one of the things that you run into is that for some of these programs, you might actually have to refactor them a little bit in order to expose their commonality, right? If you're just looking for common sub-expressions between programs, you might not be able to identify that commonality until you do some transformations on those programs. And this is where PL techniques really play a key role in actually allowing you to do that symbolic reasoning. This is purely symbolic reasoning that is needed in order to identify these common structures. And then once you have that, you have your learning phase, where you're trying to find your recognition model. You're trying to train the recognition model so that those programs that match the observed behavior are the programs that are deemed to have the highest likelihood, right? So essentially what you want to do is you want to sample programs from the language and then use those programs to look at what that program does, look at the behavior of that program, and try to maximize the probability of that program being the program that is suggested when you see that output. So I mentioned, for example, this domain of logo graphics, right? Imagine you're trying to generate programs that draw all of these different shapes, but you're starting from a very low-level language where the basic things that you have are just move in particular directions, pen up, pen down, simple arithmetic, loops, that sort of thing. So generating some of these programs in that language is going to be quite involved. But what we find is that from those programs and from those tasks, the system is able to learn routines for doing things like drawing arcs, drawing spirals, drawing polygons. But more interestingly, it's also able to learn higher order routines that are able to learn things like radial symmetry, right? Give me a function, and then I will draw the radially symmetric version of that drawing. Give me a function and an n, and I will draw that. And one of the things that is interesting is that if you look at the dreaming phase, right, this is the phase where you're generating random programs and learning from them. In the beginning, those programs look quite like garbage, right? They're not particularly interesting. But as you learn higher and higher level components, those components are actually capturing a lot of regularity in the domain, such that even just randomly drawing programs from that language now starts giving you things that look more like things in the corpus. And so by doing this, you're able to learn this hierarchy of components that then allow you to find these programs even and represent them very, very concisely. So,
okay, so the next topic is going to be safe neurosymbolic learning. So back when we first motivated neurosymbolic methods, we said that there is this option in the synthesis problem to also put in constraints of various sorts, safety constraints, robustness constraints, and so on. And to us, that's a really important feature of the space, because that's an opportunity to bring in some of the very strong guarantees that we have in the formal methods world with into this world of machine learning. And so just to go back to that picture, we had this as the problem statement that we are now also allowing an extra input, which are these additional constraints. And then when we are solving the optimization problem that's learning, I have this constraint that I want to satisfy this property. One general strategy that a lot of us are taking in this space is that we are closely coupling verification and learning. And the reason for this is that there is a lot of work on formal analysis, safety analysis of machine learning models. But there's this fundamental question of why would you expect a model to satisfy a property that it wasn't trained to satisfy, right? So for example, there's all this work on how verification, you can do verification of robustness of neural networks. But if the neural network wasn't trained to be robust, you wouldn't really expect it to satisfy those properties beyond a certain point. And so there is a lot of work on connecting the two, basically giving the learner a signal from some kind of a correctness checker. It could be a formal verifier, it could be also something statistical. But here we'll talk about just the formal verification approach. So then the idea is that you are doing certified learning. You are learning a model that comes with a certificate of correctness. And the proof could be either during learning, that every step of learning maintains some sort of correctness invariant, Or it could be that at the end, when the learner converges to a model, it finds a function, that model will have a correctness certificate. So in order to do this, you need to come up with new machinery for optimization. And let's investigate what that looks like. So the idea over here is that we are going to start with this picture of a learning agent. So sorry, this square, I don't know where it came from. But basically, the idea is that you have a learner, which has this policy. It's the controller, right, that it uses to make decisions. And it's taking these actions, it's interacting with the world, and then the world changes state, and also the agent gets a reward. The learner gets a reward. And then there is this objective of you want to learn a policy, a controller that's going to give the learner as much long-term reward as possible. So this just says that aggregated over time, you are getting the most possible reward. This is the standard picture of reinforcement learning. And now, what we are saying is that we're going to change a few things. So for one, we are going to turn the model that we are learning. The default is to use something like a neural network. That's what the standard reinforcement learning approach is going to do at this point. But what we are saying is that let's replace this by a program, which may have neural components. So let's just think about what that entails, right? Where can you apply this? Well, think about a robot which is doing some kind of interaction with the world, and it's also doing learning. And the robot has neural components as well as traditional software components. So then, this is going to represent the robot's decision making, and this is the world with which the robot is interacting. But this idea is very broadly applicable beyond these traditional AI domains like robotics. So there is a lot of discussion in the systems community, for example, about integrating learnable modules into the system stack. So folks at Google, I know they're using machine learning models inside YouTube, inside critical system infrastructure to make optimal decisions. And so you could ask that, what about all of the correctness requirements as we are doing this optimization? So at this point, the way things are done is that these modules are introduced in a very restricted way, so that it doesn't really have any implication on correctness. It's all decisions that are only about performance. But imagine a future where you do more widespread deployment of machine learning models. Then you may still want to satisfy all of the correctness properties, or you will still want to satisfy all the correctness properties that systems need. But you won't have the guarantee that the models are always going to satisfy those. So then you would need to somehow make sure that while learning, your learning algorithm is such that it doesn't violate these correctness invariants. And so how do you do such learning? The general idea over here in an emerging body of work is that your learner is now going to have access to a formal verifier. It could be a statistical verifier as well, but here we'll stick to formal. Now you are still solving the old optimization problem, but the formal verifier allows you to satisfy this component as well of the property. So what does this look like, right? What does such an architecture look like in a little bit more detail? So I'll give you one example of this that our group has been pursuing. And so the starting point here is just good old abstract interpretation, where you are propagating a symbolic representation of a set of values through a program. And for us here, the program is going to be this policy, this decision-making function. And we are pushing sets of inputs. Think about worst case sets of inputs coming from the environment, the world, and you're looking at the outputs and you are asserting properties that are going to hold when you do such a transformation. So now, as you all know, the way in which you're going to check safety in abstract interpretation is that you will do this kind of an over-approximate computation of the program's behavior, and then you're going to see if you are violating any of the key invariants that you're supposed to satisfy. But now imagine that rather than just thinking of a 0-1 correct or incorrect outcome, you had some kind of a measure that you could get out of this, a quantitative measure. So here, let's say that we looked at the volume of this overlap between the set of states that the abstract interpreter thinks is possible out of this program and the unsafe region. So in other words, what we could do by modifying an abstract interpreter is get a measure of how unsafe a particular program is. And if we could do that, then we could use that as a signal for a learner, right? Imagine now that this policy is something that the learning algorithm could tweak. But what you are telling it to do is that tweak the policy parameters so that the system becomes less unsafe. And that's the essential idea, right? Use an abstract interpreter to create a continuous signal and signal of provable safety, and then use that signal to drive learning. Now, there are important details, like in this case, the policy is just a neural network, so it's differentiable, and you could get away with this. But what if the policy had branches and so on? How would you deal with that? Well, it turns out that there are ways in which you can handle that problem. So, for example, if you have a picture like this, where you have some neural network or some symbolic pieces of code and conditional branches, there are ways in which you could propagate gradients through a structure like this. So basically, what you would have to do, or one of the strategies you could take, is that you would take these if-then-else's, which are the discontinuous bits of the program, and approximate them by probabilistic computations, which allow pushing back of gradients. So that sounds very abstract, but I can go into details offline if you're interested. And there are other strategies too. There are other ways by which you can approximate discontinuous program statements by smooth statements. Now, let's talk about the unknown world that's out there. So far, what I have talked about, this assumes that I have a program, which is our decision function, and you have some kind of a signal, right, that is allowing you to update the parameters of the program. But here's the thing: if the program interacts with the unknown world, then this is a black box by definition, right? How do you do any kind of computation of safety? How do you do abstract interpretation? And how do you do backpropagation through this world? So one strategy for this is to have something like this. You have a world, but then as you interact with the world, you learn a model of that. Now, it turns out that this is a strategy that is being used in machine learning for efficiency reasons, because each interaction with the world is expensive. But on the other hand, if you could learn a model of the world, then you could essentially simulate that model any number of times. But for us, in the current setting of verified learning, there is this extra advantage that a model of the world provides us, which is that I could now use it to do verification, to do abstract interpretation. And so that's what we've been doing. And then, of course, there's this little detail over here that this model of the world is not necessarily a sound abstraction of the world. It's fundamentally something statistical. But it turns out that you can, under some assumptions about the smoothness of the world, it turns out that you can get some statistical guarantees. Like you could say that, after a certain number of samples, you are going to be within some distance from the real world with a high probability. And then you can do sound verification with respect to that kind of a learned model. So there is another version of this problem, which is called safe exploration. And there, what you are trying to make sure is not just that the final function that you learn, the final policy that you learn is safe, but that safety happens at every point of time. So just to go back to the previous thing though, here, what you're doing then is that you're getting this signal from the formal verifier and you're feeding into the learned model, and this is biasing the search over parameters of this learned model towards functions that are provably safe. And another good thing is that at any point of time, when you are doing abstract interpretation also gives you not just this bit that it's safe or unsafe, but also you get these this proof in the form of the abstract states at every point of time, which you can check. So after you have gotten finished abstract interpretation, you also have this proof that you can check. Now, in this case, that proof only becomes possible at the end, because at intermediate points of time, you are going to potentially have lack of safety, and you're going to bias the model to avoid this sort of situation. But at intermediate points of time, this can happen. Now, what if you wanted to make sure that even at learning time, you were safe? So why would you want to do this? Well, imagine you have a Mars rover, right? You're exploring Mars. And you don't have the luxury of falling off a cliff at any point of time. You are learning as you are exploring, you're collecting data, you are updating your model. So how do you handle that problem? There are, it turns out, strategies for that as well. This problem has been studied quite a bit in the reinforcement learning literature, and it turns out that we can do verified learning modulo this kind of strong property as well. So the basic idea is something like this. So if you think of this universe of all possible policies, all possible functions that you're learning, there is a subset of that is verified. And so there is this approach called projected gradient descent, where what you do is something like this. So think of this as a representation of a space of possible functions. So each of these points, it represents a function. And as you go down these contours, you are getting a function that is more and more high performance. So it gives you more reward, basically. And so normal gradient descent would be something like this, that you would start from an initial point. You are going to take a bunch of updates, and you're going to get better and better functions in terms of performance. But here, what you're going to do is that whenever you do such an update, you are going to project back into the space of verified functions. And how to do that exactly, there are important details, but you can look at these papers, or you can talk to us later. And you can basically repeat this process, and you can do this in a way that ensures that even for these intermediate points, when you're actually collecting data and updating the parameters, you're actually doing some exploration, you're never violating whatever your correctness invariant is. And so essentially the idea is that at each point of time, you're going to do an update, but you are only going to do this with data collected safely, and then you are periodically going to project back into the space of verified functions. So you will always maintain this invariant, that whatever you learn is going to be, whatever you have at the intermediate point of learning is formally verified. So that's basically all we'll say in terms of techniques. We can discuss more offline if you're interested, but this hopefully gives you a flavor of how all of this can interact with verification. So now, just to conclude, the reality is that we are in a world where machine learning is ubiquitous, and it is here to stay. But software 2.0, as it's frequently being referred to, it's unlikely to be just neural networks. Deep learning researchers would like it to be so, but then at the end of the day, you want planes to fly, you want self-driving cars to actually not kill people, right? And so there are going to be these constraints of safety and real-world accountability that you can't just overlook. So it's likely to be, not to mention that even if there were a machine learning model that were AGI-like or whatever is the buzzword, ultimately, it has to work with human societies, and humans have to trust it. And just a neural network seems difficult to sell. I'm talking to doctors who are using machine learning. They're very reluctant to use anything but the simplest form of machine learning, where they can actually look at the model and understand, what the heck is going on with this. And at least in the short run, we are in no danger of getting too close to that general artificial intelligence. ChatGPT is very popular, but finding this kind of behavior is like shooting fish in a barrel. So really, what we are hoping here is that we are excited by the machine learning revolution, but we also want to make sure that progress in machine learning happens responsibly, and one technical way in which you can make that happen is to bring together the best of software 1.0, if you will, and machine learning, and specifically neurosymbolic program representations, in which you're bringing together symbolic programs and neural networks, and neurosymbolic program synthesis mechanisms, where you are bringing together all of these solver-based or reasoning-based approaches with statistical approaches. That seems like a promising candidate. And here we showcase the work that some of us in this area have been doing, but this idea is in the zeitgeist. There are lots of folks who are proposing ideas. So for example, Stephen Wolfram of Mathematica fame just had this blog post a few days back, where he was talking about how you can put together ChatGPT and Wolfram Alpha, which is this symbolic reasoning engine, which is behind, uses much of the technology behind Mathematica. How you can bring them together to get better results in question answering. And there are many others as well. So these ideas are, I feel, here to stay. And the question is, can we use some of the best of PL techniques, the kind that is being discussed in this conference or PLDI or other venues? Can we bring those ideas into this world? And also, could there be a good way back? Could this spur new PL innovations? And in terms of applications, we are specifically very interested in this scientific domain, but there are so many other spaces as well. Control, we showed examples of that. Healthcare, basically any place where machine learning meets the real world, and there are important constraints of interpretability and trust and safety and so on. And specifically in this National Science Foundation project that Armando and I and a lot of others, Ishil and a lot of others have, the idea is to do significant or transformative scientific progress using neurosymbolic programming. And we are looking at a whole lot of different application domains, from cell biology to organic chemistry to cognitive science. And underlying all of that is this emerging science of neurosymbolic learning that we showed some parts of in this tutorial. And with that, we are going to end. Questions?
Back to the slides of learning a model real world. It makes sense to instead have a neurosymbolic representation of the real world, where you have some extra knowledge about how the world.
Sure, absolutely. Yeah, you could instantiate that model with. So let me just go back to the slide. This one. Yeah, it doesn't have to be a neural network. It's just some function you could use prior domain knowledge, most definitely.
We talked about synthesizing programs based off like input-output pairs as well as natural languages. I'm wondering if there's any work on synthesizing problems based on logical specifications and whether that would be a good.
Absolutely. Yeah, in fact, synthesis from logical specifications was almost all of program synthesis until pretty recently. And yeah, absolutely. So for example, in these settings where you have strong correctness criteria, so you could imagine, starting with a functional specification of, let's say, a robot controller, and then expressing that specification in something like temporal logic, and then synthesizing starting with that, but also maybe refining what you are learning using data gathered through exploration. So all of that is definitely in scope. Any other questions? Yeah, and if you want to play with those notebooks, it's really, really easy. Atharva and Jennifer, our collaborator, they put in a lot of work. So if you just go to those pages, just open the collab, it's all sitting there. It's really easy to play with them.
With things like this, where we're getting guarantees on the learned models, is the focus mostly on like showing that with high probability it meets a specification, or is there also quantifying like how far it is from the optimal in the sort of like a
yeah. That is very difficult because in deep learning you have extremely difficult optimization problems, and no one really understands why it works to the extent it does. So that would be very difficult.
Okay, so yeah, no one does that.
No one really does that, I would say. Now, if you want to say that you have, let's say, a reference implementation, and you are doing at least within epsilon distance from that, that is something you could do, right? But if you are comparing with a hypothetical optimal that you don't have an implementation for, it seems extremely difficult. So actually, on that note, so I was talking to some folks at Google Brain. So one of the problems they are interested in is that, so they're sticking these neural networks into decision making for how fast to stream YouTube and various other systems decisions like that. And a lot of the times there is this problem that you have you introduce a system, a module like that, you learn, and then your performance actually goes down because there is no guarantee. So if you had some way of making sure that your performance is going to monotonically improve over time, that could make sense, right? And you could do that because that would just be a correctness property that you have a reference implementation, you want to be within epsilon distance from that. But again, hypothetical optimum comparing against that seems very difficult. Yeah?
So I think intuitively neural nets are like sort of allows highly nonlinear behavior. So how is it possible to like use say to represent the neural nets using things like constructs that are common in abstract interpretation, like interval models as well as like convex polyhedron?
Yeah, that's a great question. So, so first of all, the settings for which verification of this sort works, the neural nets are fairly small. You're not doing abstract interpretation through GPT-3. But that said, even for those, you do need to go beyond just basic convex representations. Disjunctions are quite essential. But with a sufficiently large number of disjunctions, you can model everything. And here it turns out that, yeah, you can scale it up a bit, and then you can model reasonable properties. And another thing actually related to that is that when Armando talked about distillation, so you could ask the same question. that how can I distill the behavior of a neural network into a program that is symbolic? The answer to that is that it doesn't have to be exactly a representation, the same representation, right? Or the same function. So in fact, the neural network may have learned all sorts of low-level junk that you may want to smooth out. So if you can distill a neural network into something that is kind of sort of the same, but not exactly, and it has a simple, succinct representation, that can be a feature. But so in that case, the neural network is used more as a vehicle for synthesis, if you will, because of the differentiability. You can synthesize fast using a neural network, but then once you've gotten to a reasonable point, you distill it down into a program that is close to it, but not exactly it. Any other questions? Okay then, well, our email is open, so just feel free to ask any questions that you have about any of this. And regarding the content, it's all going to be up on the webpage. Great, thanks for coming.